We've got a density operator, rho, it's positive, trace 1. So by the spectral decomposition theorem, we can write it as the sum of PI's. These PI's we can think of as probabilities, and this get run of the i's are some orthonormal basis of eigenvectors of our density operator. Now we define the van Neumann entropy to be this beautiful formula, which then became, once we worked in a little bit of work, the entropy of the PI's. We went on to prove we were defined relative entropy, so we defined between two density operators, and we used double notation here, this notation. And this by definition was minus this trace log sigma. And what we managed to prove was that this quantity is in fact non-negative, and this equality because obviously if they're the same, then here what you have is exactly S of rho. Yeah, so I forgot to mention, and I probably could have mentioned it in the last talk then, an interesting corollary from this Klein inequality, and that's the corollary we can get. What happens now if we put in sigma as to be a completely equiprobable distribution here? So if we put sigma is the identity divided by, well, we use this one. What would happen? Let's say it's the identity operator divided by D, where D is the dimension of the space. So normally for us, so usually suits the area. Well then, this would be then the S. We have from Klein. Log of the identity divided by D. But if you think about what's the log of these matrices, that's the log where you just log here the PIs, leaving this here. So all we will get here is an identity matrix with a log of 1 divided by D. So this would 1 divided by D. So this would be minus 1, sorry, log 1 divided by D. Trace rho times the identity. But the trace of rho, of course, is 1. Okay, so since the trace of rho is 1, this just gives us that the S of rho is at most logarithm of the dimension of the space. With equality, if and only if rho is basically the identity operator. Okay, so you can think of that as the same as a parallel in the classical entropy case of just having an equipolar distribution. This we will see, this we will use later, much later. So, yeah, it's worth mentioning now. Right, so we've seen this kind of relative entropy, and now what we want to do is define entropy on a composite system and see what happens when we have our comparable to conditional entropy on in the classical sense. Right, so this is going to be, that was the end of 7.4. So this is going to be 7.5. Yeah, so we're going to suppose our system of, let's say, n qubits breaks down into two lots. Yeah, so A is one part of the system of n qubits, and B is the other lot. Okay, so this is going to be a composite system. And our state is defined by some density operator on this system. So the density operator is the density we denote by rho with AB, the density operator on this composite system. Now, as we saw quite a while ago now, to describe how system is, how our state is on just the A system, we trace out, we do a partial trace over the B, and we denote that density operator by rho A. So rho A, so the state of the system on the A system is described by rho A, which we saw before is the partial trace over B of rho AB. And likewise, we saw that the B system is obviously described by tracing out over the A. Okay, so this is going to be super important, these partial traces. So let's just give a quick example. Just to refresh our memories, since it was quite a while ago. So for example, if we have A would be assist 1 to n minus 1, and B was would be just the n system. If our rho AB was something like, let's see how it is, C C, okay. Let's do So the j's just go from 0 to 1 then. We would have one of the coefficients first. Yeah, let me do it like this. Oh, I see what I did. Okay, makes sense. So what I'm doing is I'm just going to write out all 4 possibilities for the B system. Okay, so the B system's here. This is the i's and the j's describing what's going on in the A system, and then we get Cij I1 J0 plus Dij I1 J1. Okay, so that would be a typical density operator over the AB system. And then if we want to know how this is described over the A system, then we would just trace out by the B system. So that means that we take either side 0, 0, but we just look at what happens, the 0, 0 just on the last qubit, and then 1, 1. So here this one survives, so we get the sum of I0 2 to the n minus 1. Okay. And then the 0, 0 and the 1, 1 are going to annihilate this, and the 1, 1 will give us the Dij's here. Oh, sorry, that's gone now. Okay, so you just get the sum of Ai, J, Dij, and the IJs.
Okay, do the indexes, like, are they supposed to go from 0 up to 2 to the n minus 1? Like, doesn't this, like, it would make it an odd number of terms, like of i's? Like you should them from either from 0 to the n minus 1 minus 1, or how does it?
Yeah. Okay. Good point. Thank you. Mm-hmm. Okay, so the first thing we're going to do now is recall when we first introduced this density operator on the composite system. Yeah, actually, maybe we didn't do that. So yeah, we're gonna. So if our composite system is a pure state, recall that means that it's simply the ket bra of some state in a Hilbert space. Then we have the entropy of A is equal to the entropy of the B. And this is going to be because we're going to find that they have the same eigenvalues. Okay? Now, yeah, so recall that.
The number of qubits in A and B doesn't matter?
The number of qubits in A and B doesn't matter.
That's seems kind of
a strange thing. And this is Yeah, this is where Edward and I will be working on these and we'll get to it, completely entangled states, and this is important for that too, and it did confuse us for a while. I think I've got it clear now. Anyway, so recall that for a pure state. So I'm going to write site AB on the understanding that that's a pure state in the AB system. Okay. We saw we had the Schmidt decomposition. Schmidt decomposition. Way back. States that there's this orthonormal basis let's give it a name. Oh dear, awful names. IA and IB for A and B. Such that this pure state can be written as the sum of lambda I, IA, IB. Okay, using the awful notation where we run through the i's to give ourselves the basis. Okay, so hopefully Paul was sitting at home writing down nice little side i's and right i's, which would be the correct thing to do. Yeah, so what does this mean for identity operators? This would be that if we have row A as Kepler of this, then we're going to get this thing. And now you see what's going to happen. Because if you partial trace, oh, sorry, this is not what. Can't be orthonormal basis because A and B may not have the same size. Okay? Orthonormal sets. Sorry, orthonormal sets. A, I, and IB, such like this. Boom. And now when we tracing over, so extending these to bases and taking the trace.
Or you can have the lambda i's be 0, no? Just like you can extend the bases and have the lambda i's be 0. Ah, no, okay, but if they're the same size, yeah, they can't both, yeah. Like you can have the, okay. I mean, you can have them both be bases, but the sum can only has to reach 2 to the minimum.
Yeah, exactly. The sum can only go up to 2 to the minimum of the A and B.
I think I recall you writing it as bases, but maybe I'm wrong. Like when we did Schmidt, like earlier.
Sorry?
No, the like when you wrote the Schmidt decomposition, you wrote orthonormal bases.
Because when we did it in class, I assumed that A was equal to B. But then when we did it as an exercise,
okay.
it was for we did it as an exercise for
okay.
And in that case, you have to say orthonormal sets because obviously
because they don't have to be the same size. Okay.
Yeah. So now you see it, yeah. So extending the orthonormal sets to bases of those bases of their respective systems. Oops. When we take the trace, so the trace of A over A, for example, of rho AB is going to be the sum over J of J A. Sorry, and all you're going to get left with is and likewise with row A. So clearly they have the same set of eigenvalues. So row A and row B. So set of non-zero eigenvalues. So it's very, very, very useful, very strange, first time you see it. And then after a while it gets a little bit obvious, but yeah, it is. I mean, the whole point. I think the whole point of the strangeness is the strict decomposition is strange. Yeah, that you can do this, that you can write any pure state on the larger system in this way is not obvious. And remember, that's equivalent basically to the singular value decomposition. Okay, so that algebra, that theorem from linear algebra, in a way, always looked a little bit odd, that it doesn't depend on the size of the systems. Okay, so that's where this is all coming from. Okay, so there's a theorem and proof all on one board. I'll leave it up there a second. So let's have a look at our favourite example. Let's have a look at the Bell state. So the Bell state we can think of as our row AB. Oh, sorry, our side AB. So then composite row AB will be one of like this. And now when we trace out by the second system, for example, well, let's trace out by the first, so it's the same as down here. So then row B, tracing out on the first system, I have to do 0, 0 from both sides. Well, that's okay, that leaves me a 0, 0 here. 0, 0 from both sides, that's going to be 0, 0, 0, and then 1, 1 from the first side, boom, boom, and then finally 1, 1, which goes down to 1, 1. So that is just going to be 1/2 identity. And clearly this is also true if we trace out on the first symbol. So in this case, That goes about entropy. Well, so with normal entropy, we had two probability distributions, well, two random variables, and we were comparing them with the conditional entropy with
the -2, like it's gonna be a -1. It's log of 1. Like it's twice 1/2 log 1/2.
how would you? So now we define the conditional entropy for the one entropy. And here, what we're thinking of, this is the kind of like and so this is like to be compared with okay, so we kind of like argue that this is the right definition for the entropy in the normal entropy sense. It's the joint entropy minus the entropy of y, because it's the entropy that's left once you know y. So you take away the unknowingness of y here, and you get left with the entropy there of the conditional entropy. So it's in the same idea. However, things are very different, because in the case of Shannon entropy, we saw that this was always greater than 0. However, we just saw an example here. Well, you let me write down nonsense. I mean, I penciled it out, haven't I? So this, yeah, this is just. This is a pure state. I got this right, right? Yeah, it's okay. It's like you just don't see that it's a pure state when it's like that, you know, so I was getting worried. This is a pure state. So, in the above example, if we diagonalize this, it's got one eigenvector with non-zero eigenvalue, and that's itself, and that's this one, okay? And its eigenvalue is 1. So the entropy of this thing is 0. Okay, so the S of since B is a pure state. So this is 0, but this was 1. So which implies the conditional entropy is 1. So now we can have negative conditional entropy, and I think what this is trying, if you think about this example, what we're saying is there was kind of, in a way, no entanglement here. Everything was very clean, but when you look at the subsystems, in fact, it's maximally entangled in some sense, which I will find later. Okay, so we have like a completely equipolar distribution on here. Okay, and that's that's a reflection of the Bell state itself. Okay, so it looks, it's a pure state, but really when you look at it inside it, there's a lot of entanglement between the two systems. Entanglement, in fact.
And what's the intuition behind having negative entropy? Like,
what's the intuition behind?
Yeah, I mean, how can we understand like having negative entropy? Because in Shannon's entropy, zero entropy means that we know all the information of the system. But if we have negative entropy, what does it mean? That?
Yeah.
Well, what's the intuition behind that? I mean,
it's a very good question. I have no idea how to respond to that.
Because in here, if we know B, we surely know A, and we could say that the entropy intuitively is zero, right? Because we know, if we know B, we know A. But in here, being negative is like, in a sense, it's like knowing B, we know A and much more. Like, I don't know how.
Yeah.
I mean, it's more like there's nothing to know about row AB, but like any pure state gives entropy of 0.
Mm-hmm. Yeah, it's definitely not clear how we should interpret that. I guess if you spend enough time working with these things, you do develop an intuition to what it really kind of means to be negative. Hmm. Right. So now some better news. Okay, so conditional entropy is maybe not a great definition if it's going to give us something which we find difficult to interpret. Whereas we can still define quite satisfactorily mutual information. So for Shannon entropy, we had it was the joint entropy minus h of x minus h of y. Okay, so that was the. So let's see if we do the same thing here for Van Neumann, and then for Neumann entropy, we should have mutual information is okay. So now we're going to write it as with the S of row A colon row B. Okay, so what should this be? This should be the joint entropy, so that would be the entropy on the composite system. This would be entropy of the two subsystems. Yes?
Isn't it? Yep.
Okay.
It's like the sum is always bigger than the, yeah.
So what we'd rather like to show, and which will turn out to be true, is that this mutual information is indeed bigger than or equal to 0. And this inequality, by the way, is called the subadditivity. Ah, yes. Now, I was going to do this a separate lemma, but I've written up the theorem now because I was writing down the theorem as it stood in Nielsen and Chuang, and at some point they say the log of rho A tensor rho B is equal to the log of rho A plus log of rho B, which seems completely reasonable since log AB is log A plus log B. But then it's not quite so obvious, to me at least, for density operators, that such a thing would be true. Okay, so and in fact, if you go into a little bit more detail, I think you have to do so let's do a proof of lemma first. Okay, so, and then I'll prove the theorem. So I want to prove that the log of and it's not even clear that that's the right dimensions. If I write down log of rho A here, there's something wrong because this is something on the AB system. So even when I take the log, it's still on the AB system. So it can't be log A. So it's also like can't be log A. But it turns out when you do the proof, this is indeed equal to this. Okay, so let's just check this first. So suppose W's. So what's then? Okay, so the first thing to observe is that you can just tensor together the eigenvectors. And of course, when you tensor together the eigenvectors and you apply the operator, you're going to get this eigenvector eigenvalue times this eigenvalue. Okay? So when we do the log of this thing, it's the sum over ij of the log of the eigenvalues. So using spectral decomposition. Oh, I suppose I need to have this kind of version on here. And now we can split the log of the eigenvectors into two. I think that's going to be more space. I think the lemma is going to be, the proof of the lemma is going to be longer than the proof of the theorem. So, you get minus the sum over I log and I. And this is the important bit, you get the sum over j of these things. Bear with me. Okay, so the point being here now is that when we sum up the kept brass of the psi j's by the completeness condition, that's the identity. Okay, because they're an orthonormal basis. Okay, so here I get I sum. Is it still minus? Is that always been minus? Why do I put minus here? I don't know. Okay, and now this thing, of course, is just log of row A. I'm starting my defense. Okay, so we've managed to prove the lemma. We shall now use it to prove the theorem. I think there'll be no surprises for guessing. No, maybe not. It's not that obvious. We're going to be using Klein's. Let me just leave out the lemma. Yes. So we will prove now the theorem. So our row is we're going to apply Klein's inequality with the row being the row of the composite system and the sigma being the tensor product of the two reduced density operators. So what is minus? So to apply this, we need to do minus the trace of rho log sigma, which is minus the trace of rho log the tensor product minus the trace. Now we just apply the lemma here. This is log rho A tensor 1b. Now imagine here, we trace out this first term, just this bit here. Let's trace out on the B system. Okay? If we just trace out on the B system, that leaves us still with tracing out on the A system. So trace out first, so we'll split the trace into the whole system. This trace is over AB, right? The whole system. So if we trace out first on the B system and then on the A system, what happens when we trace this on the B system? Based on the fact that we've got the identity here, all we're going to do is get the reduced operator. So we're going to get left with row A log row A.
Right. Why is that? Like, why does it work out so? Like, why can't you do it separately?
Yeah. So if you trace out on the whole of the AB, what does that mean? I mean, if you think what happens if you trace out on with the B first and then the A's, and it's like expanding the brackets, you're basically.
Yeah. Like, so no, like you can do it in this order, yeah. But like, why does it work out to be row A log row A when you?
So log row A is on the first system, okay? So this bit here. So he's not affected by the tracing out on the B system.
Oh, okay, right.
And then by definition, this tracing out on the B system is row A. Because this is just the identity on the B system, so all we're doing is tracing out A, B on the B system.
Okay.
It's clever, isn't it? And this is exactly the same by symmetry on the other end. So what we're left with is the entropy on the A system and the entropy on the B system. Now, what does Klein say? So Klein says that minus, so we have S of the row 0 implies minus S of the row minus trace of row log bump is bigger than equal to 0. And that should be it because our row is row AB. So this now implies that S of row AB is less than equal to minus the trace of row log sigma, which we just proved is. Okay, so actually quite a big part of that proof was this statement, this lemma, and they just go straight ahead. I guess you just get used to these things. Okay, so let's try and not make the same mistake that we made before we did Klein. What happens in the case of equality? So Klein says, observe equality implies, so equality here implies equality in Klein. Which implies that rho is equal to sigma. Rho is equal to sigma. And that there is no correlation between the A and the B system. Okay, this just means it's just simply you've just taken some density operator on the A system and you test it with some on the B system. No entanglement, no correlation. Okay. And I think that in this case, that does have some intuition, right? I mean, the mutual information is 0 if and only if there's no correlation between the two systems.
Yes.
So in this case, yeah. So I think it's all a case of probably definitions. I don't think the conditional entropy is maybe the best definition, let's say. Yeah? Whereas I think that this one really does capture the mutual information between the two systems in some sense. So it's just a lucky thing, okay? Now, the unluckiness of the fact that the reason the condition entropy goes wrong is because you can have the situation that so we saw the cat down. This situation occurring. So, but strangely, the following is true. So, it is true. S of row A is less than S of A row C. Is this less of B like it? If you try and do it with two systems, so that is very strange. So nature will let you have, so you can have more entropy in the reduced system here. For example, this could be 0, as we saw in the Bell space, and this could be like completely 1, the maximum. Whereas you cannot have that simultaneously happening on 3 systems. You cannot have this, yeah. Yeah, so it cannot be, so let's say like we can have this. We saw that we can have this, and it could be that that doesn't make sense, doesn't it? Yeah, that's one. So it cannot simultaneously, so both of these things cannot simultaneously occur. Which kind of doesn't make sense because then you could just yeah, but it's only AB system, isn't it? It's got to be ABC system. Yeah, so it's got to be that there is some row ABC. Okay, so for some row ABC, you cannot simultaneously have this. Yeah, so you could have on a double system that the entropy is bigger. The reduced entropy is bigger than the entropy of the composite system, but it cannot be if we split it into 3 systems, you cannot simultaneously have these 2 inequalities, which is extraordinary. So we'll play with that a bit in the exercise, okay? This is called strong subjectivity. As it doesn't make sense to simply sum these 2 inequalities.
Right, but like, what does it change the fact that there's some row ABC? Like, if you could define the system like independently.
No, the point is you can't, can you? That's
Okay.
I mean, this is by definition the partial trace with respect to B of this, and this by definition is the partial trace over the A system of this.
Okay. So if you have AC and BC, then ABC must exist, or
yeah. So we're saying there's some ABC system. So this is equivalent to, and this will include the exercises. So this is equivalent to the entropy of the whole system. It's quite a remarkable and confusing result. And to prove that, I'm not going to try and prove that because it would take an entire class, if not more. And that was a conjecture for a long time, and it was proved years, decades after it was conjectured. Okay, so I could let me just have a quick look. Okay, yeah, so if you look on page 519, you'll see this one. Well, I've switched the letters around, but that makes no difference. And the other one is on theorem 11.4, okay? Yeah, well, the proof is very short, but I mean, it uses a lot of previous things, yeah, which is why. So you can look at. So you have to use theorem first. So as I say, we'll go over those inequalities in a couple of the exercises, which we'll probably do in the final class a week on Thursday, I think. If you don't, yeah, so I'm not sure about the 2 remaining exercises we have left over from exercise from BIM stage. We might, I don't know whether we'll fit them in at some point, but if we have some spare moments at the end of the class, maybe. If not, we could try and squeeze them in a week on Thursday. Okay, so let's push on, 7.6. So it's no surprises, one Neumann entropy. These things being the most weird, yeah, because it looks like here, even a non-mathematician would surmise that from these 2 things, this is not true. Well, we spent a fair bit of time looking at measurements before, so let's see what a measurement does to an entropy. So we're going to restrict ourselves to projective measurements, partly because otherwise it's not true what I'm about to say. So suppose we have a projective measurement. We project as Pi. Okay, so we've just been given some Hermitian operator. These are the projectors onto the eigenspaces. We know various things about these projectors here. So we know that Pi squared is equal to Pi. We know that Pi Pj is equal to 0. That's what we need. Okay, so. So we're supposing again, system before the measurement is described. Yeah, but you see, I'm now getting into the annoying habit of saying this is in the state row, when row is a density operator, not state. So it's a really thing that occurs in all the books as well. So I think the way to say it is the measurement, the system is described by the density operator row. Okay, to be absolutely clear that it's a density operator, and not simply a state. Then after the measurement, if we do not learn the result, it will be in, so if we, so we've set up the measurement apparatus we actually haven't measured, then it will be rho bar, which will be the sum of pi. Oh yeah, the other thing of course is these are, so it's just pi rho pi. Now, I think I probably mentioned it last time. How would the comparison be between the entropy of rho dash and rho? Intuitively.
I mean, before I would have said that it would have decreased, but now, like, since it can go from a pure state to a mixed state, then in those cases it will increase. So if there's a general trend, then
that's a very good example, Adrian. Yeah, exactly. Yeah, it can go up. I mean, I would say it go up anyway because you're more uncertain about what it's going to be like after the measurement than you were before. Yeah? So, but yeah, you're right. I mean, you could start off with a pure state, and definitely after the measurement, it's going to be the mixed state. So, yeah, that's a. Okay, so it took me a while to work out that in the book, I think they made a little mistake. I think it's a misprint, let's say. So I think what we need to do is apply. But I think in the attempt to think this conditioned on this, but I think it's the other one. Leave this. But let's see if I'm right or wrong. Okay? And I'll tell you why, because straight afterwards they say, oh yeah, the other thing we need to know, the projectors satisfy their completeness. Yeah, so now we can use now here. Is again, we need to do the minus the rho log or something, and it's minus log, sorry, minus the trace. So we need to do this minus the trace, and it's rho log rho dash that's going to be the one we want. Yeah. So let's see how what happens. Minus trace. First is first. I can sum up a pi in here, and nothing's going to happen. Trace, see how it is. Okay, now I'm going to take this sum out. And also, I'm going to put it under the squares thing. I'm now going to use the cyclicity of trace. So recall that we proved at some point that the trace of ABC was the trace of BCA. So this one of these PI's can jump down to the other end, and this will be going minus the sum of trace PI rho of PI dash P I. Okay. Now, what is rho I? Oh, sorry, rho dash P J. Okay, so if I now, oh, I just got my PA PJs as 0, right? So PI well, this is the sum of PJ. Here in PJ is 0. Okay. So this is just PJ, right? PJ. Okay, and likewise, PJ radius is PJ sum is equal to PJ, which we just showed is inverse PJ. So this log rho I Pj is equal to Pj log rho dash. Now here, to apply to go from here to here, you can either do it carefully with the just writing out over the spectral decomposition, or you can just think of these things actually as series. I mean, we haven't proved that at any point, but the fact that these exponentials and these logarithms, if you just use their normal series expansions and stick in the matrix, they work, okay? But you don't need to do that either. You can just write out the spectral decompositions. Okay, it'll be exactly the same. So this all implies this. So coming back to there, this means that minus the trace rho of rho dash is equal to minus the sum of the trace of Pi rho Pi log P dash. And now we take the sum back inside. This is minus the trace sum of P. And if I'm not mistaken, that's it, right? Because what is this? This is 0. So this thing here implies S of rho minus trace sorry, minus stress result. Good. Okay. So I think they throw those little typos in there just to waste my time. But yeah, I think that's right. Now that's going to be an extremely useful theorem for us when we try and prove the whole band, which I like to say whenever I look at it at home, hot label band, because it is a bit of a hot bound. But I don't think we're going to get time to do it today, because once we've done entropy of the mixture of quantum states, then I think that's probably going to be it. So that'll be at the beginning of Thursday. So we're going to use this fact that a projective measurement increases entropy. Well, just out of curiosity, I didn't actually write this down. What happens when we have equality then? So rho equals rho dash. So it actually really always, unless it's you simply measuring in rho itself, you always increase entropy. Okay, because you can only have equality here, rho equals rho dash, but rho equals rho dash implies that projectors the identity. The identity.
No, but like if you're measuring, like if your state is a pure state and you measure in the pure state and something else, like the entropy should stay the same, no? Like the other probabilities are 0. Like that's a case when it would be, we would have equality.
Yeah, but then everything would be 0, wouldn't it?
Oh, okay. Like a non-zero.
Yeah. Worth thinking about. Something to ponder on. It's usually these moments where I come up with an exam question, so I shall continue to think about it. Right, let's push on, otherwise I'm not going to get a chance to get to quantum supremacy, which is my overall aim. Well, so I want to do two things. I added a couple of things to the syllabus. I don't know if you've seen, because I think we'll probably just about have enough time. And one of them is the entanglement measures that we've been looking at with Edgar, and I think that's really interesting and yeah, it's fascinating stuff. And then I was reading an article on quantum supremacy, so I wanted to try and give you an idea of what Google are claiming when they claim quantum supremacy. Exactly, because now we have everything we need. We know about entropy, we know about unitary matrices, we know what a quantum circuit is. So what is it they're claiming? Okay, so it's not easy, but I think I can do it. I'm just not quite sure how long I'll need. So anyway, so now we're going to get through the rest of the formal stuff. Yeah, so yeah, we will also need these kind of mixture of quantum states. So this is the entropy of the mixture. You see, they're like quantum states, but it's not really quantum states, they're operators, yeah? So I'm going to write a mixture of operators. Right, so we're going to suppose rho I are density operators. And the pi probability distribution. And we're going to try and prove, what we're going to try and prove is prove bounds on the entropy of the composite system. So we're going to be interested in bound the entropy of this density operator. And the first one, we're going to actually do equality first. Okay, so maybe. Yeah, okay, because it doesn't come up. Okay, so let's suppose all of these density operators i.e. if so recall the support is an eigenvector of a non-zero eigenvalue. Okay, so that's just a scrolling plot. Okay, so the entropy is given by the entropy of the Shannon entropy of the probability distribution pi, and then the weighted entropys of the individual operators. And it will turn out, after we prove this, that when we do the main theorem, this would be the upper bound for the general case. Okay, so equality is when all these density operators have orthogonal separation. Okay. Okay, so let's just blast through and suppose that these things are the eigenvectors and eigenvalues. Then because of the orthogonality of the eigenvectors, the pi lambda I j is an eigenvector of this thing without sorry. Okay. Why? Because when you multiply this by this, this is orthogonal to all the other eigenvectors. So if we were to write out the other ones by the spectral decomposition as the sum of its eigenvectors, with Kepler's eigenvectors, with the PIs, and of course when you multiply by this, they'll go 0. Okay? So we can just say since rho L of I J is 0. And that's just equivalent to saying that they have orthogonal support. Okay, so it's just on the non-zero. You need it on the non-zero eigenvectors, of course. The eigenvectors of non-zero eigenvalue, because they're the ones that appear in the spectral decomposition. You see? Yes. And that should be it, right? Because now we know all its eigenvalues. So that's the eigenvalues and eigenvectors of this thing. So it's those of pi lambda I j. And now we do our favorite tricks. So if we sum the lambda i's j's over j, that's summing all the eigenvalues of the density operator rho I. But rho I has trace 1. So that's 1. So this is minus sum pi log pi. Okay, and here some of the probabilities of the i's. Sorry. Summing over I over the j's, so we get minus pi. Sum of the j's. And this, of course, is exactly the entropy of which is what we wanted to prove. Right, so it should just about give us enough time left to prove what happens in general. Okay, so this is a very special case that these rho i's had orthogonal support.
Is this like an equality case of the thing we just did, or no? It's like the one with the post measurement. Like when you measure the entropy increases, like is this case where like you have an ensemble with orthogonal supports? Or they're not the same?
You mean after the measurement?
Yeah, like a state where the like a mixed state with orthogonal supports. Is it an equality case of the?
Oh yeah, because afterwards you get the pi rho pi's, which are then orthogonal because they're projectors. Yeah.
Right, like they would only belong.
Well, I have to think about that. Yeah, it's a good point. Yeah. Yeah. Okay, so let me just work out and show you what happens in general. So the theorem in general, everything the same as before. We want to find bounds on this thing. This, what we just proved, will turn out to be an upper bound. And here, this thing will be this. So it's in fact two theorems because we need to prove both the upper and lower bounds. First. And in these proofs, especially from now on, we could introduce a kind of fake system and attach it on the end, and it's going to have orthonormal basis. I's, and so the row of the AB system is going to be okay. So we will now attach this to our thing. So we've got pi rho I tensor I. Of course, it has to be a I. Okay. Now, so what happens if we trace over A of this thing? Well, inside each of these, we're going to trace over A, the row A, B. So we've got trace over. I don't even need to write A here because it is only there. So it's just the trace of this. But of course, this is the density operator, so its trace is just one. Oh no, I think we've lost this. So that's just one. So that's just the sum of P on it. Yeah, so using my whole line, but we have to. It is clearly just the Shannon entropy of the PIs. And the row A tracing over the b's. Okay, we trace over the b's. Well, this is an orthonormal basis here, so we're just going to recover our initial density, composite density operator. Yeah, okay. So, and finally, now this will be an exercise, but actually, we kind of already saw it in the last theorem, which is why we had to prove up and down first. Okay, but then I thought later, actually, there's still something to be said. So I'll leave that as an exercise. But I think you can see that the fact if you stick these things on the end, then things start to become orthogonal. Okay, the density operators themselves become orthogonal. So you can believe me when this implies that this is indeed the case that we got last time. So we can have h of the pi's plus, what would it be? It would be the entropy here. Yeah, sorry, so plus the sum of pi. So, okay, so I think that's almost, you can see that from here and the previous theorem, but I'll leave the details as an exercise, and there's a bit more to that exercise as well, so that's only part one. Okay? And now it should be subadditivity. Subadditivity. So if we stick it all in this and this cancel, and we get this thing. Let's see what are the other terms in row A. Oh yeah, so S of row A, yeah, so there's Z of this. Okay, so the two Shannon entropies cancel in this inequality. Right. Now that was the easier bit. Now we're going to do the upper bound. We can have Applebee's service. So suppose first run along. I just use this, that is the same. Now to find the run This is going to be So, okay, so we saw from the pure state that the entropy of the reduced operators are the same. So what would happen if we tried to calculate this S of A? If we trace out, yeah, I mean, I don't want to write it all out because I'm going to trace it, because you'll see what happens. You get the cross terms are going to go when you trace anyway. So rho A is just going to be the sum of pi this. Which is the sum of rho A here. So the S of rho A is so this must be equal to S of rho B as well. And now we apply, we measure, so now we make a projective measurement. So remember we talked about doing a measurement just with respect to a basis, like making the necessary projectors. Yeah, so after the measurement, what happens to rho yeah, so we traced out on A system. On the A system, we had a trace. We measured, so yeah, so we did the measurement, so we're down to these things that are, this is the trace of this is 1. Okay, so we traced that on this, and after measurement, we got that. And we already proved that projective measurements increase entropy. So we have proved that the entropy here, that implies that this thing, which is the sham entropy of this probability distribution, is at least the entropy of the mixture here. Which is what we wanted to prove in this case, because this is then less than or equal to this. So this is like the assumption that all of these things were pure, of course, and in that case, these are 0, yeah? So right, so now let's see that they're not given. So now we're going to do, suppose, and use spectral decomposition to write this out over its eigenvalues and eigenvectors, and that gives us a probabilistic distribution Pij's. And now we go kind of like almost achieved, yeah? Because what is rho? Rho is the sum of pi rho I, which is now the sum over I and j of pi j. Let's call this thing rho ij. Rho ij. And you see now the rho ij's are all pure. And so we can apply what we just proved before. We proved for pure states that this is less than this. So now we've proved that. So from before, S of so we just got to now stick in the Shannon entropy and see where it takes us. Oh joy, almost there. So minus the sum over I and j, pi j log pi j. And as ever, we have to be careful and just see what we get when we expand the log with sum. Yes, we're just using this now because we all we did was we wrote rho I out over its spectral decomposition, and then noticed that, oh, okay, so all these things now, these are pure states. So really, I can write this sum over the sum probabilities times a pure state. It's really, really simple. Just so all the hardware is actually here. Well, let's see if it gives us the right answer. So this is now equal to minus pi log pi sum over j pi j minus the sum pi j log pi j. Okay, well the sum of pi j, that's just summing the eigenvalues of this density operator. So that's one, so summing of a probability distribution. So here we get minus the sum of this, which is just the entropy of the pi's. And then, well, here, this is exactly what we would get, what would S of PI be? That'd be minus the sum of J of PIJ or PIJ. So here, if we sum over the J's, that's going to be plus the sum over I of PI sum over J. So it's PIJ or PIJ, which is the S of the roots. Which is what I want to prove. So really nice. I mean, I didn't trick doing it for the pure states first, and then actually all the hard work was there. Once you've done that. Okay, so I shall stop the recording.